I want to give a brief review of my recent paper, the Phi UV interstellar radiation field in galactic disks. Why should you care? First of all, the UV radiation field is very important for the thermal structure of the ISM. It gives you the photoelectric heating, which controls the multi-phase ISM and potentially regulates star formation in galaxies. It may also affect the multi-phase structure of the circumgalactic medium if you're talking about clouds that are close enough to the galactic disks. Then also from the molecular structure point of view, the UV intensity is very important for dissociation of different molecules and therefore for interpretation of extragalactic observations, such as H2, CO, and other molecules. The take-home message from this paper, I think, would be, first of all, now we have a general analytic theory for the intensity of FUV radiation field in the ISM of different galaxies of different kinds, from local to high redshifts and different masses. And the UV radiation field per star form increases with decreasing metallicity because of the decreasing opacity in the disk. And finally, low metallicity galaxies, therefore, may have higher thermal pressure compared to non-thermal components like turbulence or cosmic ray pressure. So to model this, basically I followed both analytic and numerical approaches. From a numerical point of view, what you can do is just assume that the UV radiation sources are all B-star associations for which the luminous distribution is known to be a decreasing power law, and also assume exponential thin disk where the density of sources decreases with galactic radius, and then place an observer in different locations on the disk and calculate the contribution for the flux, including dust absorption. This gives you the UV radiation field as function of the parameters, the dust abundance, the star formation rate, the location of the observer, and the galactic radius. However, to make some order in the disorder, it's useful to also think of the things analytically. And to do that, you have to recognize that there are three important scales. Here, I write in the numbers for the Milky Way. And more generally, the scales are the galactic scale radius of OB stars, which produce the UV radiation field, the distance between the sources, so that's connected to the density of sources or star formation rate, and finally the dust absorption radius. Here it's just 1 over dust absorption cross section. And when you take these distances, the scales, and divide them, you can get the two key dimensionless parameters in the problems. In the problem, that's inter-source dust opacity, so the opacity between sources. This tells you how important is dust in absorbing radiation. And the dimensionless galactic radius, which basically tell you how many stars there are that are contributing to the FUV intensity if there was no dust opacity. And this is how it looks. The solution to the problem, the UV radiation field intensity, as a function of these two parameters, tau, star, and x. And these are the two regions, the Milky Way conditions, and this is low metallicity, high redshift galaxy or dwarf. This is for the reference, the more usual parameters, dust abundance and scale radius normalized to local values. And what we can see here is that first there are two regimes, one where the UV intensity depends on the metallicity or dust, and the second where it depends on the scale radius. And then also what we see is in this regime, which is more often encountered, as we decrease the metallicity, the UV intensity per star form increases as the dust opacity decreases and the galaxy becomes more optically thin. So this has very many important implications. For example, you have more heating at low metallicity because of this, which may result in higher thermal pressure. And this is all discussed in the paper, so check it out. Thank you.